They went boom, boom. Yeah. They went 2-1. Yeah. Sometimes I turn the washing machine on. All right. Okay, so I'm going to finish this section on emergence today, and then we're going to talk about statistical mechanics. So all of these things are brief touches on much bigger topics. Um, but I think it's important to sort of, you may have seen them elsewhere. Fine. If you haven't, it's very important to see them somewhere, and it'll kind of connect, it'll keep connecting into the next work, which will be robustness. This is this forest fire story, but much more general. And then this whole story of where do you allocate? I mean, this is a big deal. Where do you allocate hospitals and coffee shops based on what you're trying to do with them, right? So hospitals, you're trying to help people. Coffee shops, you're trying to help people but make money at the same time, right? It's complicated. So that's sort of a geography of fairness thing. How do you allocate voting stations? And there's a whole project that I've been trying to develop there for years, which is basically, the geography of fairness in a way, or just like sort of a diagnostic. It could be both a diagnostic of what a particular country or the globe is doing in terms of some allocation of a facility, if you like, whether it's been through governments or markets or whatever. What kind of situation are we in? All right, so there's that. And then we get into complex networks, which is rooted in all of this statistical mechanics stuff. So I want to kind of give you that flow. And it'll be somewhat historical stuff, but it will connect back to rich get richer. So there's lots of things that will kind of connect. Yeah. And then we'll get to contagion, biological and social contagion. So they're huge stories. They've been central stories to pox for a long time, from the start, and for my career, really. So unfortunately, it's all very relevant. All right. So you guys are underway with the assignment for this week. So it's a good little StatMech thing to play around with. There's we'll talk about it today, but percolation is a nice abstract model. You don't have to worry about physics, right? It's just these little random clips and things. It doesn't have to be a physical model there, but it is sort of extraction or extrusion of a physical system into a nice toy model. All right. So let me make this thing work. Okay, it's this thing. All right, so speaking of toy models, so the sort of great exemplar in social sciences, and again, if you've heard this, I think it's still important to talk about, is due to Schelling. So there's a couple of pieces here. So Schelling won a Nobel Prize, another one of these kind of interesting economists who seem to actually think about people and kind of wonder about them. He had these works of sort of 60s and 70s. Hockey helmets became a thing, right? So the NHL or whatever it was called at the time, I don't know. No more helmets, right? And then at some point they all do now, but there's a transition, there's a tough guy kind of thing or a tough human thing where you don't do it. So what's that, what can you understand that kind of transition to everyone adopting something, wearing seatbelts, right? So there's some law enforcement aspect of that. But, if you go back in time, people cut them out of cars, right? A lot of protests, it's like this horror. And, how do you cope with these? Like smoking, right? Nicotine is incredibly addictive and helps you perform better, right? It's pretty problematic. So, but it's also, kind of a disgusting ambient problem. So, and so these are sort of policy type things, but how do things also just happen organically and so on? Okay, so he thought a lot about this. He had this story, which this is where the term tipping point comes from. So you'll hear that in lots of places, but not due to him. And this is again one of these incredibly awful, dire sort of societal problems, which is about what he was thinking about was segregation, but not purposeful, but organic segregation, where you've got a neighborhood of a particular, let's say, type of person or kind of person, and it may be religion, it may be race or whatever, but there's a homogeneity to it, and then other people start to move in, And the neighborhood, this is what was called in the 40s and 50s, I believe, the neighborhood was said to tip, right? It was changed from one group to another. And that's a phenomenon that goes on today all around the world. And there's lots of, gentrification is sort of is a framing that's much more, that's on the side of the gentrify, right? It's a pretty soft, friendly. Well, it's not great, but it's certainly not in terms of framing particularly strong, right? I don't think Trump would have called it gentrification if he was against it, right? So slogans, we can talk about slogans a lot at some point. Anyway, uh, so that was his idea, and he's wondering, like, how does that happen? And again, it's this kind of Coleman story, which is, you know, you could tell everyone to leave, right? Someone could stand out, or some leader could say, like, we're all going to move. This is whatever, blah blah blah. But it seems like maybe it can also happen organically at this micro level. And so Schelling's tipping model is very famous, and he has a it's a small volume, micromotives and macro behavior. It's exactly this micro sort of phenomena leading to a macroscopic thing. This is exactly the same story for, say, fluid mechanics, right, where we have the Navier-Stokes equations. We talk about little things rubbing against each other, blah, 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 and you get tornadoes out of it. So it's that same kind of conception. It's not that societal things can all be understood like that, or all ecological things can be understood in this way as micro to macro. There's a lot of things feeding up and down, but the extent you can kind of sort out. All right, so maybe Nikki Case, are you familiar with their work? Okay, so I'm just going to play with this a little bit, but I want to point to, and Vi Hart has been a sort of a good public figure on YouTube for math in general. So this was sort of a collaboration. And so you see the framing of it. It's going to be polygons, squares and triangles, right? So Sneetches, does that ring a bell? There's the star-bellied Sneetches. It's a Dr. Seuss or one of that kind of thing, right? There's the ones with stars and the ones without. Fights. I don't know about any of these old experiments, but there's sort of these. Technology and the brown eyes experiment. Oh yes, what was that one again? It was like a teacher who will explicitly tell to students blue eyes are better, brown eyes sucks. And then the next week she'll do the other way around, and then you'll see segregation right away. I mean, so there are lots of these, and there's the whether you wear a hat or not, right? There's those kinds of experiments which apparently, may or may not hold up. Yeah, UVM, which always tells you occasionally, like, we can wipe everything off your computer, just so you know. Enjoy this laptop, but we can remove it all. It's like such a nice thing. Yeah. Sorry, that's just a separate concern of mine. Yeah. There's a video of it if you want to take a look at some point. Oh. The experiment like back in the day. Okay, I'd like to see them. And as I say, like, a lot of these things aren't holding up because it turns out, because these are stories that people will believe, right? Yeah. That's why the Dutch guy spent 10 years faking data, and I don't know, I've forgotten this guy, but he's he's a psychologist. Who is it? No. Another guy faked. He was like father of the year in Netherlands, very famous, and he faked experiments for 10 years with little stories, right? Little stories, yeah, right. Because you can tell a story for either way. What's that? My favorite example of this is the candid camera one with the elevator, where the people. Oh, they stand this way. Yeah, that's messed up. That's really wrong. Yeah. So again, and we'll talk about this again a bit later on. TV shows, you can do what you want, basically. You can put people on an island and have them all be, like trying to make out with each other, stuff that is just really difficult for people's brains. I mean, even the Great British Baking Show is probably, like a forbidden academic experiment. But, so, right. So if you want to do some social psychology, either run Facebook or maybe, do a reality TV show, and yeah, right. And then, of course, you get some academics who publish with them, like publish with people on Facebook, and it all goes wrong because they're being a bit naughty. All right, I know I'm talking about. So the idea is, and I'll just say the original Schelling model was that he got out a chessboard and put down two different kinds of coins, like 5-cent coins and 10 cents, right? And just put a bunch of them down, randomly, and then had a simple rule, right? And so you can play with this rule. So the rule was, you look at your neighborhood, you're a coin, you're a 5-cent coin, you look at your neighborhood, and if there's more 10-cent coins or more 5-cent coins, then you make a decision. And you think about the threshold, right? So it starts to get the thresholds. So this is a distilled kind of idea of social contagion is thresholds, right? So if you see a certain number of people doing something and they exceed some threshold for you, you might adopt it or run away from it, right? It starts to become serious. There's a little bit of that in disease, but it tends to go the other way. You exceed a threshold in terms of dosages, and then you get sick potentially, or you develop an immune response. So there's some, you don't want to wholesale, and people do it. You don't want to wholesale take disease models and put them on social contagion models. People will do it. All right, so let's see. So this one's, there's a rule here. You want a third of your neighbors, and if they're missing neighbors, that doesn't matter. So you want a third of them to be the same. So this one's okay, right? And this one is okay. They're all okay. This one is having trouble. Yeah. Well, they're all flat faces here, but anyway. Yeah, and we have models of that where really interest. I mean, again, you kind of get out of control. But yeah, you want to have. If everyone's the same, then we call it sort of a hipster effect. And it's like, no, I don't want to do it anymore, right? So that can give rise to some interesting behavior. So there's upper thresholds and lower thresholds. So which is in here? This is kind of. So you can try to drag one around. So this one is, struggling. If we put them there, they're happier. Put them there, they're happier, right? So of course I'm doing this myself. But this is basically the game, and I think the original little checkerboard thing, that was his simulation, right? Checkerboard. Start again, checkerboard. And then, so how do you remove the frustration from this system? You can't move those, they're happy, blah, blah, blah. So this is gonna do this. No, that's a lot. Okay, all right. So this is what we want. So this is randomly moving to find a new place, and then you can play around with the thresholds. So initially, right, it's there's a mixture of people, and then eventually you start to get these islands, and now it's okay. All right, so now you can play around this, right? So these are the frustrated ones. This is how many are frustrated. So there's a lot more movement. It takes longer, but the segregation keeps going up. And again, there was no big, right? And eventually and again, this is a very abstract toy model, but it has a big story, so that's pretty bad. The big story is that most people, the intuition was you would see this and you'd say, okay, these people hate these people and these people hate these people, right? But it wasn't. It could be just this micro story where you're not like, people don't hate the other person. They do have a preference for someone around them, and it can be somewhat low. I think this is pretty bad, right? It's less than 70%, but this is less than 45%, right? So you're happy to have a majority of people be different to you. So this is when it starts to get a little. So this is it's a toy model. We have bad intuition for this. It's a little toy model, and of course we can do it very easily now. We have this beautiful version of it. It's hard to do it with a checkerboard, but it tells you a story that we didn't intuit about collectives, right? Because we're going to try to tell a simpler story, which is not, I'm not saying that's wrong, but it's hard for us to think, and you need to do that. You need to think, oh, maybe there's some complicated system thing here. So even if you do this and then try to communicate it to other people, that's hard too, right? So even if this is the truth, you're still in trouble because telling this story is difficult, right? So this helps to have these visualizations. So again, I think we can take it down to something like this. So, you're happy for, no, have I done the wrong thing? If less than 30%, yeah. So this is yeah, I've got the right way. So this is, you're happy for like 2/3 of people to be different from you, but still that went into a segregation thing. Again, abstract model, toy model, but and you don't want to say, oh, let's govern all policy of this, but it pushes it away from individual narratives where people just think in certain ways to, they're making much less biased decisions than you might expect locally, which globally gives a what you might think is a bad outcome. Of course, these people are now they are comfortable. I mean, with this is all they think about, right? They're now comfortable in this situation, and it's hard to undo, given the mechanics of this business. All right, lots of other things, and I think down here there's some of what you were saying, right? Like this is where we have too many people are like you. You also don't want that. So, and it doesn't really settle down. So this is what you'd call like it doesn't end up with a stable point. They're just bouncing around. And the segregation is 0%. So that's and so Schelling didn't have that. So that's a simple little tweak that's not too complicated. We're not, of course we could elaborate this. We could put buildings in and trees and, like, what are we doing at that point, right? We need to keep it simple. But this seems like a small change that, does tell us something new. All right. So lots of things. There's all sorts of stuff. It really gets complicated, and you can play around with that. It's good. And then just to, okay, so you can pay money now. That's cool. I just want to see the things. I am accepting the cookies. But she does have.
Yeah, you need to go on his website.
Sorry. So lots of things. I think there was something about networks where I may have.
Yeah, there's one.
I think I may have kind of had some input into doing this, saying this was a good thing. So that's a whole networks one. Okay, CO projects, right? Obviously, these are very elaborate and hard to, build up. The parable, like the one we just showed you, that's way back. Where is that? Did I go past it? There's wisdom of the crowds. That's a different one again. Yeah. So that's about, being. It's on a network, so it's important. There it is. Okay, so it's a while now. Thank you. So lots of emojis. So these are pretty great. There are a few of these around, and you just explore them if you like. So it's really a lot of. They've done some very interesting things. Okay. All right. So this is a really important. It's very hard to make these models, right? You have to play around with things. You have to have kind of a thing you're trying to explore and understand. You have to distill it, get the essence of the phenomena, create a model, see that it shows you something interesting. So then there's going to be a sort of a bias. But if it's especially if it helps you show something that's not intuitive, then it's worth telling everyone about. So these are like little gems that people have created. Okay, I have a few other pieces in here. So the emergence, right? I've just talked about emergence, but emergence of taste is extremely powerful, interesting things. We're people. I mean, if I like to if you step back and think about it, they talk a lot about food. Food is a big deal to people, right? A lot of tombstones could be like talked about food a lot. Like that was kind of their thing. It's okay. It's okay. People like to go to meals. There was also the talking with other people, but food is a big deal. It is important, right? Yeah. Occasionally you get some douche bro on Silicon Valley, in Silicon Valley who invents Soylent Green and tries to pass off the powder thing. There's some cults around with the breatharians, some good stuff, but it's all, but food, we like food. Even, I mean, we live in a world where there's an English baking show, right? Which is amazing. The English, famous for their food. So famous. I like the current thing. The winners are there's an Italian guy and a German physicist at the moment who's very meticulous. But Okay, so this is a Michael Pollan article from a while ago, but it's you know, thinking about the emergence of taste and really kind of going, because I think in nutrition is an example where we're in this state of saying, here are the bits that things are made out of. We'll put them on the side. It's got so many carbohydrates and fat and whatever, and this is crucial to your, you know, health. It's something, right? But it doesn't really get the whole picture. So, right, so simplest food is a hopelessly complex thing. There's all this sort of stuff going on. You know, we're working at this, but it's that whole field is incredibly primitive still, really. You know, so we break it down, we study them, blah blah blah. All these, there's all these complex. You know, it's all this sort of sum of the parts sort of story. Right. So it's that same thing again, and that's going to take a long time to sort out. But people are going to make up a lot of money, and they have, and they will continue as they find the new thing that's great. You know. Right? People, well, you know, people do, they'll eat nutrient. I mean, there's a certain fraction of people who said, you know, you just eat this tube every day and you'll be fine. Like my oldest daughter is in that category. Uh, for her, it's eggs actually. Anyway, so you know, there are some of these studies, right? They'll say this, but then so you know, then you go and find them. Like we did this with meat, right? So red meat was sort of associated with some problems at some point. And those studies are so hard to do, but it was a bad story. And the flip for that was to say, well, the narrative, the way out of that was to say, oh, it's saturated fat. So then that sort of took it away from meat, and it's like also coconuts are bad, right? So there was sort of and then there was this a long time, especially in the Western world, with eating fat was just no good, right? You should not eat any fat at all. Here is fat-free ice cream, which is full of sugar, but it has no fat. It was a colossal disaster, and it continues. It was a colossal disaster. So, I mean, I don't have, you know, good. I'm not saying personally I have good solution, but I'm just trying to, you know, it's difficult. It's a difficult business. So we've had these big shifts around. You know, there's the keto world, the paleo world, because that's what they did back then. Also, probably not great to copy too much of that stuff, but you know, we're pretty sure about it when it comes along, right? The vegans. Anyway, but you know, then you know, if you have too much beta carotene, that can, right, that can too many carrots, that can cause cancer, blah blah blah, right? So this is it's a difficult business. This is from Time. You know, this is just another separate thing. There are a lot of, you know, these are the antioxidants, right? They had a real burn for a while. Like, you know, what are the antioxidants in this thing? Was put on the outside of everything. Gluten-free has been a good one recently, right? Like avocados are gluten-free. It's pretty amazing. I just love it. Anyway, you know, and of course that really matters for some people, but it's just like you can see all these, there's a bandwagon. It's like we got to put gluten-free on the side of our orange, you know, because that's cool. Yes. No, it's great. No, no, and I agree with you, but it is funny that we get to like here's an you know, like right. Yep. Yeah, no, it's okay. And it's got its own little, right, the little label, the GF thing. Yeah, right. I mean, and the vegan one, which evolved, right, has been around for a long time now, I suppose. But that will help some people avoid it, of course, as well. Okay. I think I ate a vegan gluten-free donut that my wife sourced this morning. It was pretty hilarious over near the hula section. Um, all right, so this is hard, uh, right? So this is, you know, that's a lot of stuff to put together, but this is, you know, time tastes good, right? It's not bad. A little bit. Probably if you ate a bucket of it every day, not so good. My mother her career as a home eco teacher, right? This is a lost thing. There's a home economics sign over there, I suppose. But you know, in a very traditional kind of way, like you learned how to cook and needlework, and I actually was in some of her classes now and then, and of course at home. As, you know, me and my three brothers, we all learned how to knit and cook and all, you know, all these things. Uh, but she would always say, you know, she was on top of this really. She's like, basically, you know, don't eat too much of anything. Um, and you know, fats are good. You know, there's all this madness with the sugars, you know. But anyway, here we are. So And this is the theory and practice problem. And we got to have, this is a difficult thing. I have a nice example for this in fluids soon, I think, but theory and practice. Baseball, right? It's been, what an interesting sport. But anyway, I won't talk about that. But the scientific, the analysis, the fluid people, all this sort of stuff, that's very difficult, right? It's been very difficult. And that's sort of recent work has kind of gotten to understand how some of these things move around. In cricket, there's a bizarre thing that was discovered actually by me, but also it didn't go anywhere. But the Pakistani fast bowlers. So in cricket, this is really weird. In cricket, there's two halves of the ball really, and there's a big seam, and you shine one side. So you shine one, it's made out of leather, right? So you shine one side, and the ball use the same ball. Like so in Test cricket, it's 500 deliveries or something, right? So it gets worn down. It's part of the game. Spinners, kind of like the knuckleballs, the spinners will come on later and be able to use this kind of messed up ball. But what happens if you put enough slobber on one side of the ball? Because humans, right? Put enough slobber. Not the fun. You're not allowed to use, like same with baseball. You had no funny things in the pockets or the little razor blades or whatever sneaky. People have Australian cricket got in some big trouble for that recently. But if you did that enough, then after about halfway through that kind of lifespan of a ball, it would go the other way. So normally the shiny side, you'd have a rough side and you'd bowl. I won't show you my bowling, but you would bowl and it would come out and it would swing, which is like curveball, but it'd swing a certain way. And then eventually it would start to go the other way. And it just made no sense. And this happened to me as a kid and I couldn't understand what was going on. It was kind of an amazing thing to happen. But eventually, by the 90s, it was perfected. It's called reverse swing, and you just wait for it now. Yeah, but you have to slobber a lot on the other side. What a game! But that's super weird, and it wasn't like someone walked out with a simulation and said, "I think this is going to happen. You should try it." It's a lot of people slobbering on things and some accidents happening, and because it was doing something it shouldn't do. So bumblebees, sort of famously, fluid mechanics people like that, they can't fly. They should not be able to fly. They're too heavy. Their wings are too small. And the bumblebees are like, whatever, guys, it's great. It's great. So it turns out they have some weird little turbulence things they create and so on, right, that help them stay up in the air. And they're fine, yeah. So, this is going to be, right. This is an emergence. This is an example of emergence. This is collateralized debt obligation. So this is the kind of the housing collapse in 2008. This is my understanding of finance, basically, right? So and that was a situation where you had all these things that were not the whole thing was rated highly and sold to Germans and so on, investors. But if you looked on the insides, not so good. And that's sort of true of the hot dog, right? Rated very highly as a concept on the outside, delicious. Insides, best not to know how they, yeah. And I come from a farm. I know literally how the sausage is made. I probably helped make some sausages, but yeah, the sausage is, it's a clever thing of humans have done to kind of make sure we don't waste anything, shall we say? Yeah. Okay. There's a great early Simpsons. I won't say that one. Yeah, it's pretty good.
I remember when I was young, we put like single craft cheese in it. So it gets even worse because single craft, I have no idea how it's made.
But orange cheese is not.
Yeah.
Quebec?
Yeah.
Orange cheese?
Yeah.
Oh my God. You would.
The chemical one.
Yeah, sure. Yeah. You were like the bastion of hope in North America, like maybe. I know. No, it's the North American part worked. Yeah, right. Yeah. So look, you create this thing that is delicious. I mean, people love these things, right? But the insides aren't great. So that's an interesting kind of emergence. These are things I like to push on these ones, right? Universe is made of stories, not of atoms. Actually, it's made of atoms, but our universe, our culture, to some extent, I think is in this way. So I'll push on a few of these things because we'll talk about stories later on. It's from Supernatural. Oh, amazing. I love it. So great. I'm just enjoying that. Okay, so um, I really do have an explanation for this. I really do sit in a basement and there's a treadmill and weird things. This is Pratchett, the name of my cat, and narrativium. Right, he had this kind of nice little play on this. The most common element on the disk, the standard 5 elements are earth. This is a terrible pun. Oh, joke. Fire, air, water, and surprise. Element of surprise. All right. It ensures that everything runs properly as a story, right? Little narrativium goes a long way. The simpler the story, the better you understand. I mean, this is really profound. Storytelling is the opposite of reductionism, 26 letters and some rules of grammar and no story at all. And then, so that's true, right? That somehow we make this is an amazing thing. It's an amazing thing, yeah. And, the sort of fear of written down stories early on, I mean, allegedly Plato wasn't happy about it, like the oral thing was better. It's incredibly dangerous having something written down and being able to copy it and send it somewhere else. But this is a big detail in here. The simpler story, the better you understand. This is we like stories, right? But we don't understand all the possible stories, and we especially do not understand stories of collectives. They are, we really have to figure them out scientifically. All the atmosphere stuff, oceans, planet. They don't fit into the story. We like stories that are about individuals. We're happy to explain thunder by a god. Thor, with it, and then it makes really good movies later on. After a sort of questionable 70s and 80s comic book situation, but that's we can kind of understand that. That's a pretty good story, right? So we're going to work with those things a little more, and they're going to be about individuals rather than groups. Groups are difficult, but groups really are central to human behavior. So there's this higher complexity, right? So we've kind of talked about this micro to macro thing. So there are many systems where you've got the scales are interacting with each other. I mean, think about forests. There's all sorts of stuff going on. Trees interacting with tiny things. Now we understand forests to have like a whole fungus situation doing the highway thing, which is pretty bananas. Trees are made out of salmon because of some fungus transporting some stuff. Pretty weird, but totally awesome. So this becomes harder to explain, and certainly I keep talking about fluid mechanics, but it didn't have that problem so much, right? There was this profound thing, which is separation of scales. That yes, there are all these little molecules or atoms or whatever that's in your fluid, but you can kind of go out and coarse grain and get to a continuum approximation, and it will work. Mathematics. This is Girdles' theorem. We can't prove that someone's trying to kill me or not, which is kind of his problem. He was paranoid. It's terrible. He really wasn't well. But this is a difficult business. Very famous book, Gödel Bach, this is a little picture from it, but it's this idea that here are things we can prove, and this is it's speculation, right? We're putting it onto 2 dimensions. We like maps. These are real truths here actually, but you can't prove them, and these are unreachable falsehoods, and then these are negations of theorems, right? So I mean, clearly, you have these mathematical, you're building up from these axioms, and Gödel's point was actually there might be different sets of axioms that get you to the same place or not to the same place, and and everyone went, oh no, and they're like, wow, I'm going to do something else I'm going to continue doing my math and just pretend that didn't happen. Too much. So there's a few people who are terrified, I suppose, but. And also, physicists are like, sure, guy, that's great. I mean, there's sort of a long history of physicists doing things rather dangerously, perhaps, but like, back of the envelope things, and then 30 or 40 years later, a mathematician says, that was mostly okay. But if it was in a 43-dimensional universe, it would have been bad. Okay. All right. So this is a strong form of emergence, right? So there's some from it can't be. So this is a difficult thing, analytically deduced, right? So can we actually mathematically get from one place to another? And it's been this sort of remarkable achievement that we can, that we can think at all, right? That we've had a mathematical kind of conception of the world, and we've been able to do these things like write equations, and then you've done some simple ones in this class. Maybe you didn't feel good about them, but like there were mathematical stories, right? So that's pretty remarkable. And there's this idea of this, this. So you can kind of get into a mindset where you think, oh, it all makes sense, and then you can be sort of horrified by it. Like you're like, oh, why is this happening? This is why are we able to do this? And I more and more think that we're actually what's definitely happened is that there are many analytical things we can do that have no sort of application in reality, which is fine. You can say there's all of math, right? And that's mathematicians do it. There's all of math, right? So you just sort of explore it completely. That's fine. But it doesn't necessarily overlap, and we'll see that with networks with reality or some small piece. So in some ways, mathematics becomes the street lamp problem, right? It's the looking for the keys underneath mathematics is fine, but you might not only kind of need this little bit of the street lamp, right? It might not be the whole street lamp. It's under there, but maybe some of it is outside it as well, because there are limits to what we can do with mathematical work. So, and to go back to Schelling, so we had him talk, this is a long time ago, on a contagion, it was spreading on networks, 2003 at Columbia, and it was me and Duncan Watts, and Murray Gell-Mann was this other character involved with running that, ceremonially, of course. But Schelling came up to give a talk, and he had this kind of nice anecdote where he'd been talking to I guess an aeronautics engineer, perhaps, or some kind of engineer, and talking about how, in fluid dynamics, you can model simple things. There's a lot of 2D work, which of course sort of useful, maybe some 3D work, but around really simple things like a ball. And so we spend a lot of time, we can do it analytically, make some experiments and so on. But then you don't deform, and then this was a Schelling story, right? You don't then deform that ball into a plane, right? There isn't this sort of intermediate space. Like you don't have all of the pieces in between. So you kind of you've sorted out your equations, they work, and then you're like over here and you have to do it on a computer, right? And it's just, and you aren't there's not some analytic calculation for how fast this, maybe some rough things, but you're not going to write down the whole thing, right? That you're going to use simulations for that. Okay, but you're still explaining it, you're still capturing it, but now it's computational. Right? It doesn't have some beautiful closed form expression that we kind of covered. All right. So there's some fair argument. There's this idea of a weak emergence, right? So there's some system, if we can kind of work it out, there's the system level phenomena. This is this big deal of emergence, right? It's different, but you can get it there. You can get there theoretically, right? You can get there with models and equations, whatever you have to represent it somewhere else. And then there's where you can't connect it, which is kind of like a magic situation, right? So reductionism can do this, right? You figure out the pieces. This is kind of a magic story. But it might, I'm joking a bit, but it might be just that you can't quite model a forest or a brain, right? I mean, brains are pretty weird. And it may be eventually the best model of a brain is just a brain. Like we might not be able to quite capture what's going on with this maniacal thing, just 2 or 3 pounds sitting inside our brain heads that somehow does things.
It's funny, in philosophy we'll call that like the hard problem of consciousness.
Yeah.
So like the easy problem of consciousness is like the weak emergence, and the hard one.
Hard one is yeah. Well, you can see why different cultures have come up with, obviously some of them may be fundamentally true, but different stories for why you can. I mean, it's hard. This is hard. This is a hard thing.
Yeah, but then we say neuroscientists like kind of do the easy job, so they get insulted.
Well, they're still in a very primitive time as well. They really are. I remember seeing, like in the 90s, people saying, "Oh, I have slices of brain and it sort of connects to something." It's still a bit like that. Well, the problem with the dangerous territory now is like internal phrenology, right? Like, so we're, the bumps on the head story. So we've got the bumps inside the head, and like you are a criminal because you've got a funny bump.
There's a book called After Phrenology, which kind of make the argument that fMRI is just like new era phrenology.
I mean, there's going to be a lot of trouble because we'll just do it, and we are doing it. There's evidence of, who might be, given their brain structure at 12. There are papers on this, right? That here's the probability that they have a high probability of becoming addicted to substances, for example.
But also, like in fMRI, the idea is that you can have some scan and then you get a map functions on it.
Yeah.
So like if there's activity, it must be language. But
Oh, yeah. Really hard.
Meta-analysis is just like
Yeah, no, it's right. There's a resting thing that we don't quite understand, right? So you kind of have to subtract that. All of those studies have to turn all the brains into the same shape. So that's a Procrustean kind of thing. You have to stretch it a little bit. Procrustes, I don't know if you're Procrustes fans, is a Greek bad guy who just is not a good person. Who basically decided everyone should be the same size. So they either stretch people or cut some bits off them. Yeah. Greek mythology, right? I mean, it's like Netflix, but a long time ago. Okay, so Procrustes means being a little, right. So you have to reshape the brains to fit them together. So they're all, that's a funny activity. I mean, look, we've gone through things like there's left brain and right brain, like that's still hanging around. That was a big deal for a long time. There was a big deal that you could never grow new brain cells after 18. That was just totally an accepted thing. Like, it's like drinking 8 glasses of water. It was just accepted. Surely some scientists figured this out, and this is just true. And then I don't know when someone sort of became more popular and it's like, oh, actually, that's garbage and there's plasticity and so on. Yeah, it was really accepted. It was like used like you shouldn't drink alcohol, because
is not the same as neurogenesis, right? The argument was
no, yeah. So, but there was sort of like it's done. All of these things were done. Yeah. It's just downhill from 18. It's 25 actually. That's what I'm kidding. Okay, so
Hey, I'm Jad.
I do have this thing to play. It runs for about 10 minutes. I've had it for a long time. I still think it holds up. It's one of these Radiolab things. So it's connected actually to Josh Bongard, because he was in Hod Lipson's group for a while. That connects a bunch of people here actually. But it's an interview with Steve Strogatz and then Hod Lipson. And I'll just say that I came to the US. I finished my master's on a Friday, flew to the US, didn't know anyone, right? And then on Monday, I went in and said, where is Steve Strogatz? Because he was going to be he'd agreed to be my advisor. And the person in the front thing at MIT said, oh, I said, where's his office? And she said, Cornell. And so I'm like, okay, that's great. So he didn't get tenure, and he was a sequence of people who didn't get tenure who were really good teachers, right? Who had won the MIT teaching award. There was like 3 in a row. None of them got tenure. It was called the Baker Award, I think. And it was emblematic of, and this is still true, the big research schools, teaching is just totally, like it's just a bad thing you have to do the real thing, right? They don't care. I remember another person who was in charge of this institute I was at Columbia who said years before he'd gone in to tell, I think it was at Duke, that he won a teaching award, and his chair just said, never do that again. So it was funny because it's sort of in between a liberal arts place and the super duper liberal arts places and the total R1 school things. People actually care about teaching. Anyway, just to say that Strogatz did not become my advisor, but I came to so I was a little lost for a year. That was not great. And also I wanted to think about complex systems, and I remember asking people, and they're like, no. Like, no. And I mentioned linguistics and language to one professor who became my sort of default person. His name was Malchus, which sounds pretty evil, but he's like, no, you can't work on that. So it was a bit of a struggle. It turns out the applied math department was just incredibly conservative, which is true of academia in general. But of course, now there are complex systems things everywhere there as well. So that was fun. Right. That wasn't fun.
Hey, I'm Jad Abumrad.
I'm Robert Krulwich.
This is Radiolab, and this next segment began with a simple question.
Mm-hmm. Seeing as our topic so far has been limits, and we've done body.
And we did the brain.
Now we're going to go really big.
Yeah, so we called up Steve Strogatz, mathematician at Cornell University, frequent guest on the show, and we asked him,
are there limits to human knowledge?
Yeah. And his answer sent us on a little adventure.
Is there anything that's at the limits of our knowledge is a question that a lot of us scientists worry about. And certainly the 20th century taught us that there are many things that limit our knowledge. For instance, the Heisenberg uncertainty principle in quantum physics showed us that you can't know the position and momentum of a subatomic particle at the same time. You just can't do it. It's not a matter of not having good enough instruments or not being clever enough. It's just a fundamental barrier that nature puts in your way. In logic, Girdles' theorem tells us you can't prove certain things even though they're true. So there are all kinds of limits, but those seem a bit remote from everyday experience. And yet, I think there are really important limits on our knowledge that we're all familiar with. What I'm thinking of here is our inability to think about big numbers. Because with your fingers, you've got 10, normally. So we're good at 10. We're barely good at 100. And once you start getting to thousands, millions, billions, and trillions, it gets hazier and hazier. When you hear now about the trillions of dollars in the deficit or whatever it is, the debt, that means nothing. How are you supposed to think about that? Now, when you ask why can't we understand the common cold, but we can put a person on the moon, it has to do with large numbers.
Not just large numbers of numbers, says Steve, but large numbers of things interacting.
That there are so many genes involved and so many biochemical reactions involved. Our brains are limited. Our memories are very limited. And so I worry a little bit that we might be approaching the end of our ability to have insight into certain kinds of questions.
What Steve means by the word insight is not like he found the answer. It's like that.
It's like a feeling.
Right.
Like that, oh, I get it.
The feeling you get when you really understand the answer.
Yeah, that satisfying feeling that I can see the reasoning.
I can actually feel it in my bones.
That's a very pleasurable feeling, but one that we may not always be able to enjoy.
I mean, you can see the space. Good luck.
We weren't really quite sure how to feel about this,
Right.
but then Steve said, yeah, don't take my word for it. Talk to these guys that work down the hall for me. You'll see.
Yeah, we can go right ahead.
Cool. Can you guys introduce yourself? Tell me who I'm talking to.
Yeah, so my name is Hod Lipson,
My name is Michael Schmidt. I'm a PhD student.
and I'm a roboticist.
And Hod and Mike have developed this thing,
My name is
which
Michael
does make
Schmidt.
you wonder if Steve's right. It's a computer,
Yes.
actually many.
A whole tower of computers that are all grinding away and performing calculations.
Actually, when you get down to it, it's just a piece of software, but they've named it
The Eureka.
because that's what it was designed to do, to have Eureka moments.
Maybe a kind of simpler example.
And the story of Eureka begins pretty
So let's
simply
think of
with a
regular pendulum, okay?
with the pendulum.
Just one of these things you see hanging off a grandfather clock.
Okay, I've got a regular pendulum swinging in my mind.
Okay, swinging left and right.
Now, says Hod, double it. Instead of a string connected to a ball, make it a string connected to a ball, connected to another string, connected to another ball.
Which is basically like a double pendulum. The cool thing about this is you just put it up, you lift it up and let it go.
And what you'll get, says Mike, is
Chaos. This really crazy behavior.
instead of nice and even, now you got random.
It's almost impossible to actually try to predict where this thing will move.
So what they did was they got a camera, connected it to Eureka, and basically just had Eureka watch this thing, move about crazily. And then they asked the computer a really simple question. Can you make some kind of sense out of this erratic behavior? Like, is there something in this system that always stays the same?
Tell me, what about these pendulums over time is not changing?
Because with everything, there's got to be some kind of logic in there. So you're looking for a law, basically. I mean, you're looking for the law of the double pendulum.
Yes, that's the idea.
So Eureka is there watching this
It
pendulum,
was about 3 a.m. in the lab.
and it's basically spitting out all of these different guesses.
It's formulating hypotheses.
It's getting closer. Closer.
And then onto the screen pops this simple formula. F equals ma. What is F equals ma? Is that actually the law that...
F equals ma is Newton's law of motion.
The Isaac Newton.
That's Sir Isaac to you.
It's a basic law of physics.
And one of the greatest discoveries in the history of human thinking.
Took it about a day, 24 hours. But the interesting thing is that it came up with this thing without knowing anything about physics, nothing. That's why we think that this algorithm might be able to find new laws that we don't know about yet.
In fact, once word got with Hod,
When he said, I have this amazing data, which is single-cell dynamics.
Meaning he's got this tiny little thing,
It's a simple bacteria.
really basic,
and he's been collecting this information on how it works.
on its inside.
How things go up and down. Certain nutrients increase, certain nutrients decrease over time, just like a pendulum.
But the thing is, in a cell, it's like thousands of pendulums.
There's so many parts.
Genes turning on and off.
Thousands and thousands, tens of thousands.
Proteins turning on other genes, nutrients going up and down.
It's this crazy quilt of complicated feedback.
And he wanted to know, inside of this cell, how are all of these things related? I mean, we can measure it all, we can see things going up and down and all that.
But what are the rules?
What are the rules?
Yeah.
And this, he says, is the problem for biology.
Biology is one of the least well understood systems compared to, let's say, chemistry and physics.
They're still lacking the basics.
So we said, look, Mr. Robot, can you tell us what you think are sort of the important principles governing this organism and maybe detect things that were hidden from us?
So he sent us the data, and we analyzed it. And
Well, okay, let's
Yeah,
not
what
let. Yeah,
happened?
so what happens?
suddenly, equations starting popping out.
Almost immediately.
The robot came back to us and said, okay, here's a set of 2 equations that describe your data.
Do you remember by any chance what the actual equation was? Not that we'd understand it, but just sort of to hear it said out loud.
Yeah, no, I don't. I don't have my Rain Man skills developed to that degree yet.
The important thing is that the equation was telling him things like, when this protein goes up, this other thing always goes down. And when that thing goes down, this gene turns on and then does a loop-de-loop. And when he went to his cell to check all this out, the equation was right.
These equations match the data. And in fact, they explain new data.
These equations could even predict what the cell was about to do. But, hold the champagne, there's just one little problem here. The formulas check out, but
We don't know what they mean.
you don't know what they mean.
Right.
Meaning they don't know why these equations work.
Why when this goes up, does that go down? Why when that goes up, does this go sideways? Why?
I had to first look at this and try to make sense of it. We said like, oh, okay, I think we understand. And we're like, oh, maybe we don't. We think that we're close to understanding it.
But, now we're in this bizarre situation. We can't even publish it right now because we can't just publish a equation without explaining it.
So in the end, they're in this awkward position where they've got the answer, but they don't have the insight.
And I think it's a preview of what's to come in science.
The more we turn to computers with these big questions, the more they'll give us answers that we just don't understand.
We'll be faced with this challenge of having to find ways to get a computer to explain what it found.
But that will leave us, if this really happens, in some weird position as bystanders where we're sort of listening to the oracle, but not really understanding the answer. Is there going to be a time when we can't cut it anymore? We've had this window in human history when we could not just know things, but actually understand them. That is, you could know why they were true, not just know, but to know why. And that's a beautiful moment in human history, but I feel like it may only be a moment.
Well, I don't really see it quite that sort of sad and dramatic. Because at the end, there will be simple principles to describe even the most complicated of processes.
So you have a bias that prevents you from feeling the kind of despair that Steve feels and that we were hoping you would feel.
Oh, well, I have a positive outlook.
Well, I'm just wondering about the we. Look what we have discovered, you'll say when you're an old man with your robot sitting there in a dress next to you. And the robot will be holding your hand, but that will be a cold hand. And Jad and I will be thinking, I don't know, who's the we here?
Well, I would say we is sort of knowledge. I'm just thirsty for understanding and thirsty for knowledge. Me and the cold hand holding my hand, we've accumulated and contributed to the overall understanding of something that we thought maybe 50 years ago wasn't possible. And that would be something that would make me happy.
Hi, this is Steve.
All right. So that's a while ago now. That whole thing is really interesting, right? It's limits that particular episode, it starts with story of I'm forgetting the name, but a couple of women who famously sort of finished Hawaii Ironman crawling over the line in this sort of business, right? This kind of extreme physical stuff. So there's limits to knowledge. There's also the famous Russian character who could remember everything completely. Essentially, it became eventually debilitating, right? Because you have to forget things to make meaning.
It sounds like you like in different contexts because like there's a lot of problems that are super easy to like check if they're correct, but like to produce solutions, we have no idea.
Right. So there's the MP type, like so, yeah. And of course, this just around the start of. I mean, it was connected to it, but so these are computer scientists who really want to still do the physics stuff, right? They want differential equations that explain, or PDEs that explain things. I think the universe, eventually we get to things are just fundamentally algorithmic, and they don't necessarily. Maybe you can describe some of the outer behavior with differential equations, but you're maybe just using the wrong thing. And they do include algorithmic stuff in there. But just to sort of go more what you're saying, like deep learning has taken off through this period, and we've certainly got ourselves into this strange situation where we can replicate things, somewhat, but not understand them, not have any right. Really, it's an odd place to be. No. Having done that recently, and having so the first one turns 19 today, and then the second one turns 17 tomorrow. Yeah, we wanted them 2 years apart, so there you go. So a special days for us. It kicks off the whole thing. So happy birthday to, well, names redacted. So because I know people will watch this and then what? I'm kidding. So yeah, it is strange. It's really strange. There's no question. And there are some understandings now, perhaps, of those sort of phase transition type things where you kind of like it's a big soup in your head, and then you can talk. That's that's a peculiar thing to watch.
I saw this a little bit with 42. They knew the answer, but then they didn't know what the question was.
Yeah, so it's funny because yeah, right. I mean, this is basically what they didn't quite say, but they were going to that. Yeah, perfect. Yeah, right. That's Hitchhiker's Guide to the Galaxy. If you haven't read it, they're trying to find the answer to the question. What is it?
The ultimate question of life, the universe, and everything.
What's the answer? And then they find out it's 42, and then they realize they don't really know what the question is, which turns out to be what is 7 times 8, I think. Yeah. It's very, very bad behavior. Right. So, but this is a really weird time. This is not what things were like, 50 years ago. I mean, computers were coming along, but there was no idea. I mean, AI was talked about, but it was not conceptualized, but it was not, nothing like it is now, which is still terrible, of course, in some ways, right? Autocorrect is like talking to, it's just insane. Some of the things that will happen to you on a phone. You're just like, how could you think that was close to what I was trying to write? It's just like, and how is that is that other people? Like, it's not just things that happen there that you just like, it's jarring, right? It's kind of like Watson saying, they had to, what was the thing? It was like, which American, which U.S. city, and it answered Toronto. And it's really jarring. It's something that, people do some pretty weird things. There's no question. We say some strange things, but we're maybe if we can get computers to do the same things, we'll be set. I do think when they start to tell stories about themselves, then we'll have achieved something as we sit in our vats and be used as pretty inefficient energy sources.
There's this subreddit where they tell stories about themselves, right?
Okay, we're in trouble now. But we know this, right? That they're kind of like they make play. I mean, that they're good stories, I guess is what I'm. What's it called?
Sub-simulator. So there's one.
Oh, it simulates a sub. Okay.
Yeah, so each bot is based on a sub, and then they just talk to each other.
It's exactly what you expect.
So there's, who's this? Michael Kearns, who's a famous computer scientist. So we used to connect with him a bit at Columbia. He's at UPenn, and he did this thing in the 90s where he made a little bot and put it into a chat room for AI, or for AI kind of scientists, right? So it was very sneaky. Like, he didn't say it was a bot, right? So it was interacting with people, and kept a record of all these things of like who thought it was a bot, and it took a while, but back then they got it to, they fed it it would take sentences or phrases from the Communist Manifesto, the Unabomber's Manifesto, I think the script for the Planet of the Apes. Like, it had a bunch of interesting things put into it, and based on what you said, it would try to reply with something, and then occasionally say, I'm kind of bored. But obviously, that was heading in the wrong direction right there. But I know we were thinking, it was pretty interesting. Humans fail the Turing test all the time, right? So, but the other way around is interesting, I suppose. All right, so I need to. It's really that's now a while ago, right? This is 10, 11 years ago, but it's still describing, I think, or getting at this problematic situation. And I feel like computer science has just like sailed past it and said, "Yay, I made a thing that does a thing, and it's faster than that one." That's sort of the game more over there. And that's okay, sort of, but potentially. But it's just another paper the other day. Delphi, right? I think it was. Did anyone see this? Maybe it was in the Story Lab Slack, I think. But Delphi is supposed to be a moral machine, right? It's supposed to, you ask it questions and it will give you ethical, moral answers. And I guess, I don't know how you still do this today, given all the things that have gone wrong like this in the past. But people, of course, just put in a few questions, and it turned out to be, a terrible, evil thing if you asked it the right questions. It's something. I just don't understand it. It's like, anyway, so let's replace judges or whatever who are also problematic, with these things. It's really extraordinary. So that's the black box problem, I guess I'm talking about. Anyway, so just some quick things. Just, self-organization is a term it is important. It holds up. It's a reasonable term. But basically, there's no governing thing, and pieces are coming together and creating themselves. All right, lots of things. And for us, imitation, the humans, this is a huge part of us is imitation, especially without thinking we're doing it. And I'll come back to that later on. That's kind of our great skill. We're all individuals. And then this is a difficult thing. Like, how likely is complexification? And in some ways, once life takes off, you start to get a ratchet of complexification through evolution, right? Little games and all these sorts of things that are being played out. But you have to get life, which clearly we feel doesn't happen. We're a little worried about this, right? We make a lot of movies and stories about it, but no one's turned up to say, what's up? So this is a little bit of a problem. Okay, and just look, these are simple things, but we're going to use these basic things as far as we can, but they sort of run out. And there's sort of pretty blue collar kind of things. Descriptions are going to be statistical. Statistics is incredibly important here, but it doesn't. A lot of statistical work doesn't explain anything, right? It models it or captures it, but not models it in the way that you would like in, say, physics, where you provide a mechanism to explain how something gets from something to another, which is generally what most sciences are interested in. All right, so we don't need this, machine learning, blah, blah, blah. But this is this difficult thing, and this is the sort of a chasm between this. We want to understand things like Schelling's model, but that doesn't tell you, how society is completely functioning, right? But it's important to give you different stories, different ways to understand collectives. And then, of course, you have to run the whole, do as full-scale model as you can. And so epidemiology is exactly this. The mathematical epidemiology is really stuck here for a long time, for 100 years, pretty awfully. We'll talk about it later on. And there have been a few efforts in the last 10 to 15 years, partly because the data and the computational abilities are there. And in my view, Vesmaniani's group at Northeastern has been doing the right work for a long time, over 10 to 15 years now, and we got them involved with modeling Vermont's trajectory, which was good. Okay, so we'll get to this. I know you've seen complex networks potentially in other places, but I'll give you a history of it at some point. But that was a big change, and we got a little carried away. Because people collapsed a bit onto this as complex systems are complex networks. It's not true, right? Complex networks are a subset of complex systems. And of course, data. Data is the big point, right? The big transition. Data scarce to data rich. Okay. So this is another fun little one. There's a video you can watch here at some other point. It's a science paper, but it's a good example of what you might hope. It's a perfect example of what you hope to achieve in science. The ridiculous thing, that's the name of it, How Cats Lap, right? That is the name of this paper. So these maniacs, they're MIT, one of them was watching his cat drink milk, I guess, which you shouldn't do, right? No milk for cats, right? Anyway, Pratchett is always, he wants butter. He's very desperate for butter. If you open the fridge, he's like right there. Anyway, so yeah, they do it. They do so dogs just sort of like bash away, and it just works, right? It's like there's whoop, yep, we've got to have the dog cat thing. But apparently, cats do this thing where they hit the fluid, and it makes a little column. Like pull it back up, and it makes a little column, and then they go chomp. So it's a different thing. It's a different thing. Well, no one realized they were paying them to do this, I guess. Let's say it like that. They were being fun to do other things. So, right, to your point, what happens is he's just like watching the cat, and then he goes and tells his friend or something, and they're like, okay, well, we should do it. So it becomes a fluid mechanics problem. They do some analytic work. They do modeling. They get a robot. Someone next door had a robot that's supposed to be on the space station. They make it do something else, and they make it lap. And so then they do this work where they figure out frequency and viscosity and all this kind of madness, right? They actually went to, this is a scaling law thing, right? So we've got scaling. So they went to the frequency of lapping decays as mass to the -6, and they got that from analytic work and from going to YouTube videos and looking at lions lap. It's just great. So I mean, I show it because of the insanity, but here's their little lapping robot, right, doing its thing. And it's a real, the thing is, this is a funny thing, but then you can imagine there are, maybe some uses for this somewhere else, right? There's lots of stuff that involve liquids that we mess around with in funny little ways, printing, of course, all sorts of stuff. So there's definitely a basic science thing. This is, like I'm just doing basic science, don't try to stop me kind of situation. But, it could have some other. But it's what you can do with something like fluid mechanics. There are fundamental equations. We have the ability to do these simulations. We can do experiments, and you get that kind of triangle of things working together. And then there's empirical stuff. So this is what we want. And we're usually so far apart, when it comes to social phenomena, we've got theories. And for a long time, like completely no data, really, not much, just some, certainly not at the scale of other sciences. And experiments, very difficult to run. We've tried things where we run large countries with given operating systems for decades and hundreds of years until someone stops that operating system from running, perhaps. They're sort of weird natural experiments. All right, okay. I know you. It's easy to explain this, and you're doing it in your problem set this week. But this is a statistical mechanics. I'll talk about it a little bit more because I know we're going to run out of time. But this whole field is pretty weird because just the framing, right? So it's a sort of well, not quite an oxymoron, but it's something that it's a bit nonsensical because mechanics are like, machines, they do this, it goes here, boop, boop, right? Statistical, it's, now we're adding some randomness and weirdness. And, this is the stuff that's certainly had all this success early on for thinking of gases and fluids, all this sort of stuff. And marched out somewhat, magnetism marched out into other spaces to try and understand, maybe be able to explain some more complicated things that are outside of physics, right? The physicists are a little too carried away in terms of the ability, what they think they can do, I suppose, in terms of modeling everything in the world. But anyway, so this model, it's very simple. The idea is percolation. Here's an open pore, if you like. An empty space means you can travel through it. And percolation means that you could percolate, like if you put fluid in one end, it would come out the other if it was oriented. That's the percolation thing. It is from coffee, which is basically how academics function. It's the drug of choice for academia. And so that's you can see how it all connects together, and everyone was very excited. And there's no physics in this, right? I mean, I just sort of give you a physics story, but there's no physics. You just turn one on and off according to some fixed probability and then look at it. So this is a randomly created structure. There's a very simple dial, open or close from 0 to 1 at each spot. And, the question is what happens? Like there's no giant component here, and now there's a giant component in that. There's a large macroscopic piece that's connected together. And one way of thinking about it is that you can travel through from one end to another, and you can't do that here. So it's a nice little thing to play with. It's going to have a couple of nice properties that you are working on figuring out. Sorry, I got things a little bit out of whack here. Leg is catching. Good news is the injury's moved into a different location, so that's good. But there's if you look at the distribution of cluster sizes here, they're well behaved, like they're sort of right. There's nothing large in them, so it's sort of an exponential type distribution. You get to a point where there's a power law size distribution, in the large scale power law size distribution. So we're excited about that because we see power law size distributions everywhere, or we claim we do. So this has always been a bit of a draw for people, that at that phase transition where a giant component appears, there's a power law size distribution of component sizes. And people have tried to sort of suggest that that's where everything comes from in the real world. That's not true, but it's an important thing to point out. And we'll kind of address it when we talk about forest fires. And anyway, so these are a charming little model. The network, the lattice matters. The lattice matters, which is weird. This is a thing with a microscopic. So if we have a hexagonal lattice or some other kind of regular lattice, it will change the percolation point. And so that's a bit of a upsetting piece, but just that's what it is. Okay, so good. All right, so office hours again at 3. Is that right? Yes. The thing goes. All right, happy birthday, you too.